Mrs. Hoakraby and I decided kind of to start today or tonight's notes here for you guys to see an example again from earlier today in class, as well as the video you watched last night, just because I think it's good to see it again.
It is good to see it again. And your assignment that we're going to be doing in class tomorrow has several different things on it that include some previous material as well.
Yeah. So this is good, and this is also good practice because you're going to see a quest over this. Mm-hmm. All right. So and these can be kind of tricky. I wouldn't say it's so much the algebra skills, like we're pretty good about. It's just interpreting it. All right. So when it says find all possible solutions to x, I'm noticing that I'm dealing with a triangle. I don't know any of the side lengths of the triangle. So really, technically, we're trying to figure out what could these sides be in a sense if we're really finding this out. Which means the triangle inequality theorem is going to come into play. All right, so we're thinking along the line that any two sides added together have to be greater than the third side. Okay, right. So how many different inequalities do we need to set up?
We're going to have 3 different inequalities.
Okay, so like the one we did last night with you, you're going to set up our 3 different inequalities. So let's, Ms. Hoakraby, you set up the first one.
Okay, so let's start with 3x minus 1 plus our x plus 1 has to be greater than 2x plus 1.
And guys, these are good ones to kind of even maybe pause for a second and try this out on your own, okay? Mm-hmm. And then check with us.
Especially since you guys know how to do it now.
Yeah, you do. So it wouldn't be a good idea. It wouldn't be a bad idea to see that. I should say it wouldn't be a good idea. All right, so let me give a little bit of space, and you go ahead and set up the next one for me.
So let's do x plus 1 and 2x plus 1 should be greater than our 3x minus 1. And for that last, let's do 2x plus 1 plus our 3x minus 1 is greater than our x plus 1.
So any two sides added together have to be greater than the third. All right, so let's do a quick solving of this. This is going to be, what, 4x?
Greater than 2x plus 1. Subtract our 2x with 2x greater than 1, so x is greater than a half.
Okay, so star that because we might need it.
Okay.
All right.
So 3x plus 2 is greater than 3x minus 1. Ooh, if I subtracted 3x from both sides.
You get 2x is greater than...
No, just 2 is greater than negative 1.
Or 2, sorry.
Yeah, there's 2. No x. So that's probably not going to be helpful to find a value of x.
No, if it says find all possible solutions of x, well, this isn't going to help us. Yes, 2 is greater than negative 1. This is true. This is one where any solution for x would make this true, but we know, because this is involving a triangle, that not all of these not any value for x that you can think of will make this work. So this one's probably not going to help us. So I'm just going to mark through that and say it's not necessarily wrong, it's just not helpful. And I might even make a note for you guys so you know that. It's correct. The algebra is correct. It just doesn't help us with our geometry problem.
It doesn't help us to solve for x. Okay. So this last one, we've got let's see, 5x, ones cancel, is greater than x plus 1. So 4x is greater than 1, so x is greater than 1/4. Okay. Now, as I look at this, I don't see x is greater, or x is less than anything.
So we don't have that kind of upper bound restriction.
So that means that there is no upper bound, right?
Exactly.
That I could have lots of possible values of x, but we need to really kind of focus on just the lower bound.
Mm-hmm.
Okay. Now I'm thinking back to what we did yesterday. It said if I kind of made a number line just to get a visual of this, we have x is greater than a half and greater than a fourth. Well, a fourth goes first, and then a half. And I know that it's going to be greater than both of those, so I would be shading, all those greater values. And I noticed that there are things that are greater than a fourth that are also going to be greater than a half, but if I just use that greater than 1/4 category, it's not going to meet the requirements for everything needing to also be greater than 1/2.
Because this region right here
does not
work for the greater than 1/2.
Right. So that x is greater than 1/4 is actually not going to be something that I'm going to want to use here because it doesn't, there are numbers in that criteria that do not meet another criteria.
I like how you said that. So that really means the answer to this would just be
x is greater than a half.
And again, you could also, if you need to interpret it, kind of check a point or check a value. Like a number, I'm thinking between these two, 1/4 and 1/2, would be like 1/3. And if I put 1/3 in for x here, 3 times 1/3 is 1. 1 minus 1 is 0. You can't have a side length that's 0.
Right.
So again, you could test it if you're needing to see it. So 1/3 is greater than 1/4, all right? But because it doesn't work out, that's another kind of supports why what you said here would work out. Okay?
Okay. All right. So let's kind of do a quick little exploration of what we're going to be looking at, I guess we could say.
So the new stuff.
New stuff. Moving on to this last section in chapter 5. 5.6, it says, which side is longer, AC or DF? Now, I want you to notice, first of all, what am I comparing here?
Okay, well, I'm comparing side lengths, but one thing I'm noticing right away based on the fact that kind of relating to what we just did, there's 2 triangles in this picture.
There's 2 triangles. Okay, so yesterday's stuff was all dealing with one triangle.
Okay.
Inequalities within a triangle. Today we're going to be kind of looking at 2 different triangles, and we're going to notice some relationships that happen within these triangles.
Okay, so which side is longer, AC or DF? So I'm looking at the 2 triangles, and I remember from last section, when you relate like a side, when you don't know the actual side lengths, you're kind of relating it to the angle it's across. So I'm noticing that it's across from those angles there, the 112 and the 80. The other thing I'm noticing, and within those 2 triangles, I have some tick marks for the side lengths. So I noticed that AB and EF are congruent, and BC and segment DE are congruent. Probably important that they're labeled there. Does that mean those 2 triangles are congruent? No, because the angles between them aren't. So these aren't congruent triangles, which obviously means that AC or DF are going to be one of the longer of the 2. We don't know yet. I'm leaning towards the fact that AC is going to be the longer of the 2.
And what makes you think that AC is
Because I'm kind of thinking back to what we even did yesterday, is that it's across from the larger of the angles. 112 is bigger than 80. And the fact that those sides that make up those angles kind of are the same involving each triangle. So the AB and BC, AB is congruent to FE, and DE is congruent to BC. Since those are congruent sides, if you don't change those, but you make them wider or smaller, then that would kind of go along with what we learned yesterday.
Right, exactly. So, and that's absolutely right. And we're going to be learning a theorem here in just a minute that supports that too.
Okay.
Okay, so now look at what we've got on this next set of triangles. We still have the 2 sides that are marked as congruent.
Okay.
Okay. But here I'm not giving you the angle.
So I'm giving, but it's kind of similar to what we did.
Similar idea. Now we're
the side
determining
length.
which angle, T or D, which one do you think is larger?
Okay, well, I'm looking at the side it's across, which is given, which is helpful. And since GH is the longer of the 2, that means the side angle across from it, angle T, has to be the longer, or larger, sorry.
Right. And that's absolutely right. And that's getting ready just to kind of explore and lead into this new theorem.
And it actually has a name.
Yes.
It's called the Hinge theorem. All right. So one thing to notice that we're dealing with inequalities still, but we're having to deal with 2 triangles. So because there's 2 triangles, there's a little bit more information you have to have. All right. So you still have to have going back to the slide, you had to be provided these congruent pieces before you could do anything with it. So notice even in the theorem it says something about that. You can't just compare the side across or the angle across until you have that set up, okay?
So you have to have something in common before you look at what's different.
Exactly. All right, so the Hinge theorem, and don't worry about memorizing the name of this. It's more, can you apply it, okay?
Right.
So it says, if 2 sides of one triangle are congruent to 2 sides of another. All right, so this is kind of what they have in common. So 2 sides are congruent to 2 sides in another triangle. So you can kind of see that in this picture. And the included angle of the first triangle is larger than the included angle of the second. So in this picture, notice they're giving you segment RS and segment WV are congruent. They're giving you ST and WX are congruent. So and you're given some angles provided, the actual measures. So obviously angle S is larger than angle W. All right?
Right.
What is it going to conclude? And we kind of already, hopefully, you're probably predicting this. It says the third side of the first triangle is longer than the third side of the second. Right? And it kind of is talking about that relationship. So which side would we say is longer than the third? Because the other sides that are labeled, we know are congruent kind of to each other in a sense. So which side would be longer than the other?
So RT would be greater than the VX.
And this is all based on the fact that you have some congruent sides to begin with, angles that are provided, knowing that this 100 degrees is obviously larger than the 80. This side is across, and that one's across from that, and this is obviously larger than that one.
Right. And guys, this theorem, this is one where I think about the hinge theorem. Think about a hinge. Think about like a door. When you go up to a door and you open the doorway does not change length. The length of the door, or the width of the door really, does not change lengths. What's changing is when you open that door, that angle between the door and the door frame is increasing as you open the door. And it's decreasing as you close the door.
Exactly.
So obviously, as the angle is increasing, the distance between there also gets longer to where you can actually walk through the door.
Exactly.
Because if the door is closed, you can't walk through it. If the door is open just a little bit, you probably can't walk through it. You have to open it wide enough that your whole body fits through.
So like these are like your hinges. These are not changing.
They're fixed.
They're fixed. It's, are you opening it wider or are you opening it smaller? And that's kind of support that. All right. Now, the converse of this, I'm just going to go throw this out here. Same idea in a sense. Converse means you kind of flip-flop the conclusion and the hypothesis. So still notice you still have some fixed things. All right. Notice in the picture you have two pairs of congruent sides, and it even starts that way. Two sides of one triangle are congruent to two sides of another triangle. All right. Then you also, or not say then, I shouldn't say then yet, and you know stuff about the third side. If the third side of one of the triangles is longer than the third side of the other. So in this picture, notice AC is longer than DF. We can then be able to say something about the angles that they're cross. Right. So they're saying the included angle. Now, what do I mean by the included angle?
So the included, we talked about that term before. It's between the two congruent sides that we know.
So that would be like angle B and angle E. But also notice that those are the angles that are across from the side that we know that are different, not the fixed side, the ones that are the same. So in this case, they're saying that that included angle is larger than the included angle of the second. So which angle would be the larger of the two?
Here, the measure of angle B is going to be larger than the measure of angle E because the side across from it is larger than the side across from the angle E, along with the fact that the other two sides were fixed.
Exactly. Yeah, you have to start with this beginning stuff. Kind of.
So if they don't give you that you have two congruent sides, we can't really use this.
Exactly. So there's not much that we do with this, all right? And so you're going to see some of the examples. There are a lot of like quick responses. So you might even kind of maybe pause it and kind of maybe see if you can answer it on your own and then check your answer with us. Okay?
Okay. All right, so Mrs. Palermo, as you look at this, do we have enough information to really be able to compare these missing sides?
Well,
or I should say these unknown, nothing known about these two
Okay,
sides.
so the one on the left, I'm noticing that they have two pairs of congruent sides, which that is exactly what we need to even consider this hinge theorem or the converse.
Exactly.
And I'm also noticing that they're giving you some angle measures.
And it's the angle that's included in between.
Mm-hmm.
Perfect.
And we're trying to relate the sides that are across from it. And so they're trying to compare AB to DE. And so I notice AB is across from the larger of those two angles, so that means it's longer. So greater than.
Perfect. Okay, what about this next one?
Okay, I see one pair of congruent sides. I do see a side that they share, so that means that's technically congruent by reflexive.
Exactly.
So, and then the angles that are labeled are the included angles. Now, we don't know their measures, but we know that that's the angle we're relating. And I know angle 1 is across from 14, and angle 2 is across from 15. And I'm relating angle 1's measure to angle 2 So angle 1 is actually smaller, so less than angle 2 because it's across from the smaller sides.
Perfect.
Or side.
Yes, smaller side. And I love that you use the reflexive property on that one too. So notice that we're still tying in some of the ideas that we've done before, kind of in their very easiest sense sometimes,
Yes.
but this is not necessarily rocket science,
Yes.
but it is just making sure we can relate those missing parts.
Okay, so a couple more scenarios like this. So kind of, again, the relationship between, notice angle 1's measure to angle 2. That's what we're comparing. All right, so talk to me about what you're noticing.
Well, I do notice that they have the 1 tick mark already for each one of those. So I know one set of congruent sides, but then I also notice that there is another reflexive side. So I know that they do share that common side. Now, as I look for the sides that are across from the angles that I'm finding, angle 1 is across from the 8, and angle 2 is across from the 7. Well, 8 is definitely bigger than the 7. Pardon me. So I know that angle 1 must be greater than the measure of angle 2.
And if I said, what's the relationship between angle 2 and angle 1, you'd say angle 2 is
Less than.
less than. So it just depends on which one's first, in a sense.
Right.
All right, take a look at the next one. What are you noticing?
Okay, I noticed that I have, oh, look at this one. I've got 2 sets of congruent corresponding sides, but I also noticed that I have an angle between each of those sides that are congruent, that are the same measures.
So what does that mean?
I'm looking at that side angle side. Doesn't that mean that those 2 triangles are congruent?
So what does that mean about the side that it's across here? What does that mean about FG and
Those
L?
triangles are congruent, so those opposite sides are congruent, meaning that their measures are equal. So when the 2 angle measures are equal, then those opposite sides will then also have to be equal.
Exactly. And that, again, starting with the fact that you had to have those 2 sets of congruent sides, those kind of fixed measurements, and then you look at that included angle, and Ms. Hargrave noticed that they're the same measure, so then that means, of course, the sides across from them would be the same.
All right, last one. Which of the following is a possible length for DF? So we're trying to just look at segment DF. And looking at these 2 triangles, Mrs. Palermo, what do you notice?
Okay, well, I see the 2 sets of congruent sides. I see, let's see, I see some angles that are included between those. There's a 60 degree and then there's a 130 degree. And I also see that they're giving you AC's length. Which is, we haven't been doing that. We've been just kind of comparing that side AC to DF. So
I'll tell you what, let's first just compare those 2 sides then, like what we've been doing.
Yeah, I like that. Okay, so I know, based on what we've been doing, that AC is actually going to be less than DF.
Right, and why do you know that?
Because AC is across from the smaller degree angle.
Right.
Right? So ACS will be less than DF, but we're talking about DF, so maybe I could say DF is greater than AC.
Love that.
So that means DF has to be greater than 10 because AC is 10.
Right. So if it has to be greater than 10, could it be 5?
Nope.
Could it be 10?
No, because it has to be greater.
Greater, not greater than or equal to. So the only possible scenario here?
Is 15.
Is
Now,
15.
is that saying that DF is exactly 15?
Nope, it's a possible length. I want to emphasize that. It's a possible length.
Good deal.